Swayam Prabha. Digital India. Educated India.
Now, we will move on from looking at rigorous elasticity based solutions to vessels like this, structures like this, to an approximate equilibrium based approach, okay, wherein what we are doing now is we are looking at thin walled pressure vessels. Okay. What we have is essentially the same domain, it is a cylindrical structure with the end closed. This can be viewed as a cross section of a gas cylinder or cross section of an aeroplane kind of a thing, okay, wherein the ends are closed in both the cases. So, you are interested in finding what are the stresses that are induced in the structure with the condition that Rm by T is greater than 10, preferably around 15 or 20. Okay. So, Rm by T is, it is a very thin wall structure compared to the radius of the structure. Okay. Now, how do you analyze these structures? What are the stress components that will be present? We saw from our thick walled cylinder solution that the predominant stress that is present is the OOP stress. So, I have to estimate first the OOP stress. So, to estimate the OOP stress, I have to induce or I have to make a cut such that the OOP stress comes out of in the free body diagram. Okay. So, what I do is I cut here like this and like this, okay, which will be a cut made in the cylinder like this. This is the cut I am making in the cylinder. Okay. So, once I cut that, what will I get? I will have the OOP stresses, which is the circumferential stresses exposed. Okay. So, the free body diagram will be okay. If I section this, the free body diagram of this will look something like this, where I expose the OOP stresses, there is external pressure acting like that and internal pressure acting like this. Okay. Now, I want to write the vertical and horizontal force equilibrium, wherein my x and y axis are x and y axis. Okay. I want to write the vertical force equilibrium for this structure, sigma Fy equal to 0 with upward acting force as positive. First, let us look at the OOP stresses. Okay, that is the stress, so I have to multiply by the area first. Okay. Now, I am going to write the equilibrium equations for this thin walled pressure vessel, First I am going to write the vertical force equilibrium, which will give me the OOP stresses. So, I have to find what is the net force acting in the vertical region because of the OOP stresses. The net force would be sigma OOP into T, this area, this width along which the OOP stress acts. I am assuming the OOP stress is constant over the thickness of the cylinder, which is a reasonable assumption given that the vessel is thin walled, okay, and then it acts over a length L of the cylinder. So, that is into L, that gives me the force. Now, I have to find the component of this force along the vertical direction. I know that if this is theta, this angle is going to be theta, and hence and the OOP stress is tangential to the cylinder cut surface. So, this angle is going to be 90 degrees, and hence the OOP stress will make an angle theta with the horizontal, and hence the vertical component would be sin theta. Okay. Now, to this I have to add what is the effect of the inner pressure Pi. The Pi inner pressure acts at an angle phi. Let us look at an angular orientation phi from the center of the cylinder circle. Okay. So, basically I will have integral, I would write the component of the stress along the vertical direction. So, that will be Pi cos phi, and the horizontal component is going to be Pi sin phi, because it makes an angle phi with the vertical direction, it being normal to the surface. Okay. So, I have Pi cos phi, which is the component of the applied pressure along the y direction, into I have to multiply by this distance in here, which is Rm times d phi, Rm times d phi, okay, into the length of the cylinder again L, okay, and this I have to integrate from minus theta to plus theta, because I am measuring theta in the anticlockwise sense in one side and clockwise direction in the other side. So, this will be minus theta to theta, and this stress acts in the positive x y direction, and hence it is positive. Similarly, for the external pressure I have minus, because it acts in the negative y direction, you can see that the component of these stresses would be Pe sin phi and Pe cos phi, vertical component. Okay. So, that will be Pe cos phi into Rm d phi into L in the same argument, using the same argument, this will be minus theta to theta, this has to be equal to 0. Okay. From here we will get that sigma OOP into T, L gets cancelled out, integrating cos phi you will get it as I left one more component, there will be, I took the component of OOP stress in one side, there is OOP stress on the other side too. So, that should be multiplied by 2 there, okay. Yeah, and OOP stress is acting in the downward direction, so there should be a negative sign in there, okay. So, basically I have minus 2 times OOP stress into T into sin theta plus Pi minus Pe, I cancel the L out, Rm cos phi, if I integrate I will get it as sin phi, integrated from minus theta to plus theta would be 2 times sin theta, okay. This would be equal to 0, and from here you get sigma OOP to be Pi minus Pe into Rm by T, okay. So, that is the OOP stress, okay. Now, let us see what happens to the horizontal component. I will just show what happens to Pi sin phi Rm d phi integrated from minus theta to plus theta. This will be Pi Rm cos phi from minus theta to plus theta, which is 0 because cos of minus theta is cos theta. Okay. That is intuitive because on either side of the center line, either side of the center line of this structure, the direction of the horizontal forces is opposite to each other. So, that will get cancelled out. Okay. So, the Hoops stress is given by Pi minus P into Rm by T. Okay. So, that is the Hoops stress. Next I am interested in computing what will be the axial stress. In other words, this Hoops stress is nothing but sigma theta theta. Okay. I am interested in computing the axial stress, which will be sigma zz for this structure. Okay. To compute the axial stress, what should I do? I have to induce a different cut. I have to induce a cut which is vertical. I have to induce a cut like this, so that only then the axial stresses will be exposed. Okay. Now, let us analyze what happens when I cut the cylinder like that. I cut the cylinder like I showed before, I will get okay, that is a cut surface. So, basically I will have this stresses exposed, which is sigma zz, okay, and then I have pressure acting like this on this wall Pi and pressure acting like this on this lid there, which is also of pressure Pi magnitude. Okay. Now, and you know that this from the center line of a cylinder, this radius is Rm. Okay. So, now what happens? I am going to write the equilibrium equation along Fz equal to 0, taking this as the positive direction. If you recollect, our orientation of the axis was, the axis of the cylinder was z, the vertical axis was y and this axis was x. Okay. So, I write a force equilibrium along the z direction, which will give me sigma zz into thickness of the cylinder into this sigma zz is going to act over the circumference of the cylinder. Okay. There is the circumference of the cylinder on which it will act. So, that circumference of the cylinder is given by 2 pi Rm there. Okay. That is, it acts over this circumference, acts over this entire circumference. Sigma zz is going to act like that over this entire circumference. Okay. So, that is 2 pi r into T, that is the area, that is the cross sectional area of the cylinder on which sigma zz acts. Okay. Now, this has to be balanced by the pressure exerted by this Pi on the lid there. Okay. So, what happens is now this minus Pi into, it acts over the circular area pi Rm square. Okay, the internal pressure acts over a circular area pi Rm square, where it is this area that we are talking about, it acts over in that area, and hence it is pi Rm square, this has to be equal to 0. Okay. From here you get sigma zz or sigma axial stress to be Pi Rm by 2T. Okay. The external pressure can or need not cause an axial stress. Okay, that depends upon the arrangement of the vessel and so on. So, basically that is why we did not consider external pressure P to produce any axial stress, because it is in general it will not cause an axial stress. Okay. Okay. So, sigma axial now is half of the hoop stress. Okay. You have to recollect that this axial stresses will arise only when the cylindrical vessel is closed at both the ends. This is not like what we had for thick walled vessel, the effect of Poisson's effect, wherein the hoop tension is causing a contraction in the axial direction, which you are prevented by making it fixed along the axial direction. Okay. This is a stress that arises only when the cylinder is closed. Okay. Okay. Now, we have found the stresses. Next, what we are interested is we are finding the displacement of this pressure vessel. Okay. So, displacement means I have to estimate the strain. You know that strain is given by the constellation for strain in terms of stress is given by 1 by mu by E sigma minus mu by E trace of sigma identity, and now then you have to find out what this sigma is and what this epsilon is in terms of the displacement field. Okay. Now, sigma we have found there is a hoop or circumferential stress, there is a axial or shear axial or sigma ZZ stress. What about the radial stress? The shear stresses are 0. So, I know that this is 0, this is 0, this is 0, I know this is hoop. The circumferential stress I know this is 0, 0, 0, sigma axial stress is what is here, sigma ZZ. What about the radial stress? Radial stress will vary from Pa at the inner surface to 0 at the outer surface. It being thin walled, you assume that there is no radial stresses induced in the vessel. Okay. That is an assumption we are making, otherwise you have to distinguish between inner surface and the outer surface and do appropriate computation. Okay. So, we will assume that the radial stress is 0 for thin walled vessels. Okay. Now, for this you will find that sigma epsilon RR, the radial component of the strain, which we found in the previous lecture, that this is related to the displacement of dur by dr. From the constellation now you will find that it is minus mu by E sigma hoop plus sigma axial. Okay. So, this is minus mu by E into 3 by 2 pi Rm by T. Okay. Epsilon theta theta, which from the previous lecture we found it as ur by r, that is the change in the circumference divided by the original circumference of the cylinder. Change in circumference would be given by 2 pi Rm plus ur, the radial displacement of the center line of the vessel, minus 2 pi Rm, the original circumference of the cylinder, divided by 2 pi Rm. Okay. Okay. So, this will be equal to ur by Rm. From the constellation it will be sigma hoop by E minus mu by E sigma axial. Okay. So, from here you get u of r to be Rm times by E into pi Rm by 2T into 2 minus nu. Okay. Or this will be pi Rm square by 2 Et into 2 minus nu. Okay. Similarly, epsilon ZZ, which was epsilon Z, the axial contraction that we had from axial contraction or expansion that you will see, is given by, from the constellation is given by sigma axial by E minus nu sigma hoop by E, which is nothing but pi Rm by 2 T E into 1 minus nu. Okay. Okay. In all this I assumed the external pressure to be 0 in these cases. Okay. So, up to consolidation the relationship remains same, but afterwards to find the expression for ur and dur by dr I assumed Pe to be equal to 0. I assumed Pe to be equal to 0 in these derivations. Okay. Okay. Now, it is clear that what u of r is. U of r is the radial displacement of the cylinder. So, I can associate with this circumference change, but what is this dur by dr or what is this radial component of the strain? The radial component of the strain gives you what the change in thickness of the cylinder is. This gives change in thickness of the cylinder. Okay. That gives you the change in thickness, this gives you the change in radius, this gives you the change in radius of the cylinder. Okay. And this gives you the change in length of the cylinder. Okay. So, basically what you have done is we have analyzed thin wall pressure vessels. Okay. There is one more concept that you have to understand, what happens in a composite thin wall cylinder. Okay. So, let us spend some time in understanding the composite thin wall cylinders. Let us say the inner cylinder is made of steel and outer cylinder is made of copper, and there is a inside pressure that is applied to this composite steel, and let us assume that this is our interface, let us assume that this is R E R0. Okay. So, basically now we want to analyze what happens to this composite structure. Okay. The Young's, you know that Young's modulus and Poisson's ratio of steel and copper are different. So, basically how do you analyze this structure is you draw the free body diagram of steel and copper, exposing that there be a radial pressure acting at the interface of steel and copper. Okay. So, you isolate the steel pipe from the copper pipe, this is steel and this is copper, and you expose the interfacial pressure. You know that there is Pa acting here, there is Pa acting there, and you expose the interfacial stress, radial stress P interface acting like that. Okay. Similarly, there will be a P interface acting in the copper like this. There will be interfacial pressure acting like that in the copper vessel. Okay. So, now you solve this problem either as thick wall cylinder or thin wall cylinder depending upon what the Rm by T ratio is. Okay. And you have to enforce, you can solve this problem, find a displacement field, you can solve this problem and find a displacement field, you can solve this problem and find the displacement field. What is required is the displacement of the interface, what you require is ur at r equal to r interface of the steel must be same as ur of copper at r equal to r interface. Okay. The radial displacement at the interface has to be the same. Okay. That is because it is a perfect bonding between steel and copper, and there is no possibility of steel penetrating copper or steel opening up from the copper bonding. Okay. So, you have to have this condition that u of r of steel and copper has to be the same. You use this condition to find the P interface, the interface pressure, okay, because otherwise you have sufficient boundary conditions to find the displacement field in a thick walled cylinder or in a thin walled cylinder. Okay. So, basically this is how you have to proceed when you have a composite cylinder, either thick walled or thin walled. Okay. With this we will conclude today's lecture. From next lecture on we look at how to formulate the limits of applicability of the constellation or the failure theories in general. Okay. Thank you.